to see inside your heart,
Yeah.
see how it's working, and even predict like problems
Right.
before they even happen.
Wow.
That's the incredible promise of LHMF, or the longitudinal hemodynamic mapping framework. We're doing a deep dive on the research into this technology and how it uses something called digital twins,
Okay.
which are basically like virtual models of your cardiovascular system.
So what's so intriguing about this is that it's all about shifting from a reactive approach to heart health, where we treat problems after they happen, to a proactive one where we're constantly monitoring and potentially preventing these issues before they even become noticeable.
So let's unpack this.
Yeah.
First off, why is this such a big deal?
Right.
We all know that heart disease is a major health concern, but what's wrong with the way we're currently approaching it?
So the issue is that traditional methods often only give us like a snapshot of what's going on in the heart. It's like trying to understand a movie by looking at a single frame.
Okay.
They're missing all the subtle changes over time that could signal a problem down the road.
So LHMF is like hitting play and watching the entire movie.
Exactly.
And we're getting like a more comprehensive view.
Exactly. LHMF can simulate millions of heartbeats.
Wow.
Which provides like a continuous stream of data that lets us detect these tiny shifts in blood flow dynamics that might otherwise go unnoticed.
That's incredible.
Yeah.
It sounds like this could change the game for diagnosing and treating heart disease.
Right.
But how does it actually work?
So at the core of LHMF is this deep understanding of hemodynamics, which is the study of how blood flows through the circulatory system.
Right.
So think about it like this.
Okay.
We're using these complex mathematical equations called the Navier-Stokes equations to model how blood, which is a fluid, moves through your arteries and veins.
So it's using math to create this simulation of what's happening in our blood vessels.
Precisely. And to solve those equations accurately, LHMF uses a really sophisticated numerical technique called the high-order discontinuous Galerkin method.
Okay.
And this method is especially important for capturing the complex geometries of our blood vessels with all their twists and turns and branches.
So it's making sure the simulation is as realistic as possible, even down to the smallest details.
Exactly.
Wow.
And what makes this even more powerful is that LHMF doesn't just rely on this mathematical model.
Okay.
It also integrates data from those wearables that so many of us are using these days.
This is where it gets really interesting.
Yeah.
So it's taking information from our smartwatches and fitness trackers and using it to personalize the simulations.
That's exactly right.
Wow.
Your heart rate, your blood pressure, your activity levels,
Right.
all of that data feeds into the model,
Okay.
creating a dynamic simulation that constantly adapts to your changing conditions.
So it's like having a virtual twin of your heart that's constantly learning and evolving based on your own unique physiology.
Precisely. And we're not stopping there.
Okay.
The potential of implantable sensors, which could provide even more accurate real-time data from within the cardiovascular system, is something that's being actively explored.
So we're taking personalization to a whole new level with this.
Yeah.
But I imagine there are challenges in making all of this work smoothly.
Of course.
Like, how do we even know if the data is right?
One of the main hurdles is ensuring that the data from wearables is accurate and reliable. Sensor noise, which is basically interference that can distort the readings, and data latency. Those tiny delays in transmission can affect the precision of the simulations.
So it's like trying to listen to a radio station with static or a phone call with a bad connection.
A perfect analogy.
And it makes it hard to get like...
Yeah, researchers are developing techniques to reduce noise and minimize latency, but it's an ongoing challenge.
Okay, so that makes sense.
Yeah.
Are there any other limitations we need to be aware of?
Well, the sheer amount of data that LHMF processes is another hurdle.
Okay.
Simulating millions of heartbeats requires immense computational power.
So it's like trying to run a complex video game on an old computer.
Exactly.
It just can't handle it.
LHMF relies on something called high-performance computing, or HPC, which uses powerful supercomputers to handle all the calculations.
It's fascinating to think about the technology behind the scenes that's making this all possible. Now, I'm curious about how this translates to real-world applications.
Okay.
Like, how is this actually being used?
One compelling example is how LHMF can be used to understand stenosis, which is the narrowing of an artery often due to plaque buildup.
So it's creating a virtual test environment to study how blockages affect the heart.
That's right. LHMF can simulate stenosis of varying degrees to see how it impacts blood flow. It can calculate things like pressure gradients, flow velocity, and wall shear stress, which is basically the force exerted by the blood on the artery walls.
So it's helping doctors understand how severe a blockage is and where those areas of high risk are located.
Precisely. By identifying those areas with high pressure gradients, turbulent flow, or low wall shear stress. LHMF can pinpoint the spots most vulnerable to plaque formation or rupture.
This is starting to paint a really clear picture of how LHMF can change how we understand and treat heart disease.
And what's especially remarkable is that LHMF can adjust the simulation to match the unique physiology of an individual patient, making it even more powerful for personalized care.
So we're not just talking about general recommendations anymore. This is really tailored to each person.
Exactly.
This is all incredibly exciting, but I also want to make sure we're being realistic.
Yeah.
What are some of the limitations we need to keep in mind as this technology continues to develop?
Well, you're right. It's important to acknowledge that LHMF is still an evolving technology. One of the biggest challenges is ensuring that the data we're feeding into the model is accurate and reliable. Even small inaccuracies in the data from wearables can affect the precision of the simulations.
So garbage in, garbage out, as they say.
Exactly. And another limitation is the computational complexity of these simulations.
Right.
Even with high-performance computing, it takes significant processing power and time to run these models, which can limit their accessibility, especially in areas with limited resources.
So there's still work to be done in terms of making this technology more efficient and accessible.
Absolutely. But despite these challenges, the progress being made in LHMF research is really encouraging.
Okay, that's good.
And one of the most exciting areas of development is the use of virtual reality, or VR, to visualize these digital heart twins.
Okay, this sounds like something straight out of a science fiction movie.
Yeah.
Are you telling me we can actually step inside a virtual model of our own heart?
That's exactly what we're talking about. Integrating VR with LHMF allows doctors and patients to see a 3D representation of the cardiovascular system. Imagine being able to see your heart beating, blood flowing through your arteries, and even pinpoint potential areas of concern, all in a virtual environment.
That's incredible. I can see how this would be a game changer for patient education.
Precisely.
It would make the risks and benefits of lifestyle choices much more tangible.
Instead of just telling someone that smoking is bad for their heart, you could actually show them how it affects their own virtual heart in real time.
Wow.
It would be much more impactful than just talking about it abstractly.
It sounds like a powerful tool to motivate people to take better care of their heart health.
Absolutely. And VR is not just for patients. It can also be incredibly valuable for training doctors and surgeons.
Oh, I see. So they could practice complex procedures in a safe virtual environment before performing them on a real patient.
Exactly. It allows them to hone their skills, explore different approaches, and gain experience without any real-world consequences.
Wow.
As VR technology continues to advance, we can expect these simulations to become even more realistic and sophisticated.
This is all so fascinating.
Yeah.
But I'm also curious about how researchers make sure these simulations are actually accurate and reliable. You can't just create a fancy model and assume it perfectly reflects what's happening in a real heart.
That's a crucial point.
Yeah.
Validation is a critical part of LHMF development.
Okay.
Researchers use various data sets and performance metrics to rigorously test the accuracy of the simulations.
So they're basically putting LHMF through a series of tests to make sure it's up to snuff.
Exactly. One approach is to use synthetic data sets, which are essentially sets of data generated using the mathematical equations that govern fluid flow.
Right.
It's a way to test LHMF in a controlled environment where the answers are already known.
So it's like giving LHMF a math quiz to see if it can solve the problems correctly.
That's a great way to put it.
Okay.
They also use in vitro data sets, which come from experiments conducted in labs using physical models of blood vessels.
So they're actually creating miniature circulatory systems in the lab and comparing LHMF's predictions to what they observe.
Precisely. And finally, they use clinical data sets, which come from real patient data obtained from medical imaging techniques like CT scans and MRI.
Right.
This is the ultimate test, comparing LHMF's simulations to what's happening in actual human hearts.
It sounds like a really thorough process.
It is.
Are there specific metrics they use to assess how accurate LHMF is?
Absolutely. They use metrics like the root mean square error, which measures the difference between the values predicted by LHMF and the actual values observed in the data.
Okay.
They also look at the correlation coefficient, which measures how closely the simulated data matches the real-world data.
So the goal is to ensure that LHMF's predictions align as closely as possible with reality.
Exactly. And this validation process is ongoing. As LHMF is refined and new data becomes available, they continually retest and reevaluate the model to ensure it remains accurate and reliable.
This level of rigor is reassuring, especially given the potential impact this technology could have. We talked earlier about how computationally demanding these simulations are.
Yes.
Can you dive a little deeper into the role of high-performance computing?
Of course, LHMF wouldn't be possible without high-performance computing, especially when it comes to simulating millions of heartbeats. These simulations involve solving complex equations for every single point in that virtual cardiovascular system. And that requires an immense amount of processing power.
So it's not something you could run on your average laptop?
Definitely not. We're talking about supercomputers and large-scale cloud computing clusters that can perform trillions of calculations per second.
That's some serious computing power.
It is.
How does HPC actually help with these simulations?
So high-performance computing allows for parallel processing, which basically means breaking down the simulation into smaller tasks that can be run simultaneously across multiple processors. Imagine having a team of thousands of mathematicians all working together on the same problem.
I see.
That's essentially what HPC allows us to do.
So it's like dividing and conquering the complexity of the simulation.
Exactly. And this drastically reduces the time it takes to run these simulations. What might have taken weeks or even months on a traditional computer can now be done in hours or even minutes thanks to HPC.
That's incredible. It sounds like high-performance computing is really unlocking the potential of LHMF.
It is.
And as computing